if you have to spend time on designing and optimizing manually for every problem you have and deploy it onto the device, that's not going to scale, right? So our researchers focus not on manually figuring out how to optimize the neural network itself. They focus on innovative ways of doing AI.
All right, everyone. Welcome to another episode of the TWiML AI podcast. I am, of course, your host, Sam Charrington. And today I'm joined by Murali Akula, Senior Director of Software Engineering at Qualcomm. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Murali, welcome to the podcast. You began your career with more of a traditional software engineering focus. Tell us a little bit about how you found your way into machine learning.
Thanks, Sam. Excited to be on the show. Thanks for having me. Like you said, I'm a software guy, and I started working on wireless software stack. I worked in the beginning a couple of commercial products and commercial teams. Then after that, I joined the corporate R&D group, which is a research group, and I was part of the 4G research team. So at Qualcomm, when you're talking of 4G research, we build the entire system. We bring it up OTA, which is over the air, and test it out properly, uh, and make sure it works in real world constraints. So we have this mindset: unless you build it, it's not real. So we build things that can scale into the scalable and deployable. For example, you start with the radio and the hardware, the firmware, the software, all the layers, top to bottom. And we do this before even you go to standardize or commercialize it. So this is entirely a pre-commercial setting. We build the entire thing. So that's what I was doing for a while, part of the 4G research team. Then late 2000s, the first of the Android smartphones was coming out. My boss was Jeff Gellar at that time. He came on this podcast a couple of times. So he suggested that I look into smartphone user experiences, and he connected me to a team which was looking into latencies in wireless protocol and how we can improve the smartphone user experience. I started looking into the smartphone, and beyond wireless, there were so many components which we built into it. And also during that time, new applications were showing up, and there's so much going on, and I was really amazed about so much technology we packed into this platform, and I really wanted to work on the entire smartphone user experience. So that's what happened, and it was a lot of fun. After that, I continued on machine learning projects. When we did that, it was before the deep learning took off, and over time, it's become more and more deep learning. So that's where I am, doing software engineering and AI research today.
Awesome. And so tell us a little bit about your role today and the team that you work with.
I have a broader organizational responsibility as a head of the corporate R&D software engineering team that is looking into forward-looking efforts across the AI spectrum. My day-to-day, where I spend most of my time, I lead a software team in a cross-discipline effort for AI research. So researchers, applied ML folks, software, hardware, testers, we all sort of work together in a cross-discipline effort. And we apply the same mentality which I talked about earlier in other research efforts. Unless you build it, it's not real. So we build out the technology that comes out of our AI research and prove that it can be deployed onto devices. So that is broadly the role we have. And on one side, to make that happen, we are working with researchers jointly. And on the other side, we are working with the commercial teams to be always ready. So by doing this, looking at the entire system, building it out, we are in a unique position to figure out how or when our innovations can go into our products. So we look at the entire full stack for that.
Can you elaborate a bit on the full stack? I know from our past conversations that's a concept and a terminology that's important to you and the team, but it's also something that we throw around in the industry, quite a bit.
So when we talk about full stack, let me start about what happens when Qualcomm is looking into AI technology, right? We have a lot of research going on to advance fundamental AI for applications that are going to be running on Snapdragon platform either now or in future in different products. When you are innovating new ways of doing AI, researchers run the experiments on servers which run in racks in a data center, and it's all good because you can run lots of experiments and get good results, right? Now the innovations which come out of that from this big compute, uh, how do you make them run on the resource constrained devices? Okay. The software which runs on the device, the hardware architecture, the software, the tools which you use to deploy them onto the device, all that is different from what you did, the software which you used when you actually uh, ran the experiment. So that's the one which I call the full stack that is needed to deploy your AI innovations onto the devices. So we will have to look into the entire full stack. So research into the full stack is extremely important for us. We need to continuously improve every layer of this full stack and build it out, and also show that it is real, and it can be deployable. And this keeps us ready all the time so that any innovation we have, we can actually deploy into the uh, real world devices. So that's what we do. We continuously look at this hardware software full stack and figure out how to deploy it onto this resource constrained mobile devices.
Yeah, when I hear you talk about that lifestyle, I think a little bit about, I guess, Docker and where the container technologies came from, developers running things on their desktops and, trying to get it in a prod and it not working. And they say, hey, it worked on my machine. And, uh, in a lot of places, those same kind of container technologies have been adopted for machine learning, workloads. But there's this whole other set of complexities when you're talking about mobile and devices. Um, not just kind of the runtime, but the constraints that you alluded to earlier in terms of power and other things. Can you elaborate a bit on, when you think about devices in particular for machine learning, what are the constraints? And maybe, I think we're all kind of familiar with, them as users, like, hey, not a lot of memory, not a lot of compute bandwidth issues, but there's some non-obvious things, or like, how do you think about that as an engineer who works on this stuff constantly?
Yeah, it's interesting you mention how people build applications and deploy them in Docker containers. There is no Docker container on the device. But there are applications which are running in real time, right, very efficiently, and with the neural network efficiently mapped to the hardware. There's many constraints on the device. It's not, first of all these mobile devices, they run on batteries. They're mobile, right? If you take a smartphone or a VR headset or a autonomous driving car, power efficiency is extremely important. That is, I would say, almost number one. Real time latency is important. When you're running experiments on the server or even applications, for example, you can run it in batch mode on data. But when you're running on the device, uh, as the signal comes from cameras, you need to be making inferences in real time. Again, you need to know that this is not the only thing which is running on the device. There's a lot of other things which are running too, and they all have to run in real time. Latency is extremely important. Area is a big concern. The chip size, for example, the size of the block accelerator which you're using, the memory sizes, they are all important because in a way they impact power efficiency and latency. You can add more area and get the better latency, but you'll be trading off against power, right? So area is a big concern. The number of sensors, the resolution, uh, the number of applications which you are running, the tasks, everything is just increasing. The size of the neural networks, and we need to pack more and more compute, and you can't just keep increasing the chip size, right? So area is very important, and how you run it on the machine learning accelerator, using the on-chip memory versus going off chip. When you actually run the neural network, you have limited on chip memory. You can increase, but it's going to cost, and area and power, all those things come into picture. So on chip memory. So there's many constraints like that when you run, and it becomes extremely important that how you optimize the neural network to deploy and properly map it to your hardware resources, uh, and the entire software, hardware, to look at, we look at all that and develop techniques on an ongoing basis how to optimize your neural network for deployment. So this is the neural networks are going to continue to get complex and complex, right? And we need to make them smaller and efficient and deploy them.
I know from prior conversations with folks like Jeff, who you mentioned, there at Qualcomm, as well as folks on the research side, that techniques like quantization and compression and related techniques are often a subject of research there. Are those the main types of things that you are applying when you're talking about getting these complex models working on mobile devices, or are there other things? How do you think about that landscape and process?
Yeah, I think what you mentioned, they are very important. Those and a lot more. We are looking at, when I say entire full stack, it starts from the top. Um, we work very closely with the researchers. So our researchers, when they design the network itself, they are looking at what are the parallelism uh, in this design which we can uh, exploit, and how do we design this so that it can run efficiently on a resource constrained device, right? It starts from there, and after that, uh, you come up with a good design for your architecture. And how do you train so that you can deploy it onto the uh, device. Normally, if you train freely, it becomes pretty complex. uh, One example of how to train for deployment onto the device is neural architecture search. While you are designing your uh, neural network, you could use neural architecture search to get the best optimal architecture for your design, right? So that is next. And once you have the neural network, then how do you deploy it, right? You get the best accuracy, and how do you deploy? When you deploy, these are the couple of things which you mentioned already. uh, we run on integer hardware, uh, and when you train, you're training in floating point. So quantization techniques are important, and compilation. How do you optimally map the tensors to the memory, and how do you map the compute to the instructions of the hardware accelerator? So those are important. So that is the next step, right? How do you deploy? And then how do you run on the device? When you optimally compile this onto the device, the application, the stages, the sensor data coming from the camera, how does it get moved into the accelerator? What are the pre-processing stages? Then you run the neural network. What are the post-processing stages? So that entire application architecture is next, and then the hardware architecture, right? So all of it. Um, so that's what we look at when we say, looking into full stack. Um, so I'll also mention one other thing which is extremely important, right? Um, I might have alluded to this in previous efforts which I mentioned too. So it takes a continuous research effort, not just to design the neural network, but also to design tools and techniques which can make deploying them onto the device important. So we do a continuous research into full stack with a mindset that our research, in a way, is running on real devices on an ongoing basis. Okay, we sort of connect that, being in the middle. We look at everything: hardware, software, algorithmic layers, and all that, and also the we collaborate with everybody, because research is happening in universities, research is happening in our research teams, and even in product teams a lot of innovations are happening, so we sort of connect the entire dots there.
Can you maybe take us through an example of, when you think of a complex model that's coming out of research, what that looks like, and how you kind of walk this process that you identified for getting it onto a device?
Yeah, sure. Monocular depth estimation is a application which we recently implemented and demonstrated. uh, I can walk you through that. uh, Monocular depth estimation is about creating a depth map of the scene in front of you. So this is very important for many applications.
Thinking like autonomous vehicles, or as one example.
Autonomous vehicles is one example. Even mobile phones, when you are pointing at something and you need to detect features of the face.
For focusing, for in the camera, for example.
Yeah, lot of applications like that. And VR headsets, drones. Drones are going at high speed, so you need to detect obstacles very fast. Uh, so in your autonomous driving example, how far is the car in front of you in the scene, and how far is a pedestrian or an obstacle. So all those are very important. And depth estimation is creating the depth map. We need to infer for every pixel in the scene a depth value, how far it is. And monocular depth estimation is about applying a neural network and inferring this depth map from a single camera image. Monocular depth estimation is about single camera image.
As
Uh,
opposed to like you've got some control environments with cameras all over the place that you can interpolate to figure out depth.
exactly. Yeah.
Yeah.
So that is the application, and we implemented it on the device and demonstrated. We took it around the time for NeurIPS. Uh, so when we implemented that, then I can explain how we went through the process. So what happens is, when accuracy is extremely important in this use cases, right? Researchers can get the best accuracy, but through those experiments you can end up creating very complex models. Then what ends up happening is, it becomes so complex, it becomes almost infeasible to deploy it on the device. And there are bunch of state of the art neural networks which can achieve that. So what our researchers did is, they working closely with us and also working on an ongoing basis with this on device mentality. uh, our researchers designed a neural network where at training time they increase the complexity, but that doesn't translate to inference time. So because of that, you can get best accuracy at training time, but you can still run it on the device. So that's where it starts, right? As I explained.
Yeah, I think part of what you're saying is it starts at research. Like there are ways to do this kind of depth estimation, but the complexity of the resulting models is such that they're not feasible starting places for something that you eventually want to run on device. So you're kind of starting at the algorithm level with the thought of, hey, this eventually needs to run on a device.
That is correct. Yeah.
Mm-hmm.
I mean, you could just say, "Oh, I can just add more layers, right, or increase the complexity and get." But we know what happens if you do that. So our
Yeah.
researchers have that mindset. So it's a very important innovation to be able to increase the training time complexity, but not let that go to the device. Right? So that's what our researchers did. And after that, we have a neural network, and we take the design, and the full stack team next uh, took that. Uh, Even after that, right? Our inference per second speed was 23 FPS. So that's not going to make it real time. So the next step was to make the model smaller, and our full stack team used neural network architecture search, NAS techniques. To reduce the size, we have NAS tools which we use. So that is the next step. Now you make the model smaller. The next step is to deploy it on the device. To do this, you need to quantize it. Some models quantize well, some models don't quantize well. In this particular case, we have to apply our AIMET techniques, post-training quantization techniques, to make sure we don't lose the accuracy. So that is the next step. And after that, we use our compiler tools and compile it properly so that it can be mapped properly to the hardware which we have. And the next step is application design, right? We design the application properly and run it on the device, measure on device performance. And we have an integration team which tests it properly and make sure everything is stable. The application, the architecture, the tools, any improvements which we made. And that is the entire process of how you take one of the use cases like monocular depth estimation all the way to the device.
Let's dig into all that. You mentioned the first step is the algorithm. Can you share a little bit more detail about the algorithm that was developed?
It's called again the technology is monocular depth estimation. Our researchers came up with a method called X-Distill.
X-Distill?
Yeah, I'll summarize it. There's a lot of
And we'll
information.
of course link to the full paper in the show notes.
Yeah. So what they did is I earlier gave a hint that our researchers increase the complexity of the network while training, right? So the way they did it is they added semantic information um, that increases the complexity of the network, but that semantic information is not needed on the device. So you don't need to transfer that network down, and the training also happens in a self-supervised manner. So this is a summary of what they ended up doing. um, to use extra information, increase the complexity of the network, but that extra information, which is semantic information, is not required to be transferred onto the device. So the method is called X-Distill method. So that is the first step, which our researchers were able to come up with this innovation.
You mentioned the next step was applying neural architecture search. Even before you do that, you invest all this time and research, like coming up with a more efficient algorithm. Like, why do you need to go through the next step? Is it, do you have predefined performance targets that you're trying to hit, and you kind of go as far as you can with the algorithm, but you're not quite there? Or is there I'm thinking of like some kind of efficient frontier of like where you get all your efficiencies from to overuse efficiency maybe?
I think that's an excellent question. So think of it this way: but we already have that in our AMET toolkit. Okay? So we didn't have to get into, they were able to design the end-to-end system in a way where it can actually run on the device. They're looking at the complexity of the network while they're designing it. When we are working jointly with them, being in the same team, software engineers working with the researchers, we looked at the end-to-end architecture, and we found that this entropy encoding and entropy decoding could be a bottleneck. The reason it is we can exploit the parallelism in the neural network and map it to our accelerator. But when you do entropy decoding, when you need to decode a symbol, you need the previous symbol. That means you need to decode the previous symbol. It sort of serializes the entire thing. So you have this wonderful neural network part which can be parallelized, but the resulting latents, you end up serializing it. So we discussed with the researchers, and uh, then they looked at the latents and the mathematical properties of it and figured out how can we parallelize it. And they figured out that latents are actually either independent or conditional independent, and they were able to figure out how to design a parallel entropy encoder and parallel entropy decoder. So once they did that, we took that and implemented it on the CPU. Snapdragon platform is a heterogeneous platform. We have the accelerator, we have the CPU, we have the GPU, we have DSPs. So we were able to implement the parallel entropy decoder on the CPU and match the parallelism which is happening on the accelerator, and then we are able to get it to real time.
A lot of our conversation thus far has been focused on trying to achieve like inference latency targets and other inference oriented um, objectives on devices. Is there anything that you're aware of looking at more of the like training on devices? Is that a thing yet?
It is a thing. Uh, so over the past number of years, uh, the full stack on the device was more about running inference workloads, while training was mostly centralized and on the servers. So the full stack accounts for optimizing the inference, the forward pass on the device. Uh, but lately, past couple of years, or even a little more, we are seeing more and more training on the device using the local data. Primarily for personalization reasons, you have some data which is very unique to you. You can personalize the model for yourself. So those kind of use cases have already been deployed and they're showing up. So training is becoming a important part of the full stack, and we are looking at it. So we at NeurIPS 21, we actually implemented a federated learning system for distributed training completely on the devices. Nothing is happening on the server except for getting the incremental updates from various devices and combining them. So we implemented an end-to-end federated learning training system. So that is also part of our full stack effort. Um, and it requires a lot of software engineering. It's a distributed system. So you need to make sure the entire architecture works well, and it works for both PyTorch and TensorFlow users. We created libraries on the device. We created connections to a coordinator running in the cloud, so that everything scales up to thousands of devices.
And is the idea that like AIMIT and DONNA and some of these other tools that it kind of just goes into the bag of tricks, and the next time you need to build a model that could benefit from distributed training, you can apply this? Or do you think for in the near future it will require that manual kind of handcrafting that we've talked a little bit about?
Yeah, so the goal is to avoid anything manual which is not going to scale. So we
Sure.
continue to build these tools. They are going to become automatic more and more. And the federated learning framework, we package it certain way that our teams who want to do federated learning can just take it, run the experiment, but also be able to deploy without having to do a lot of work themselves.
Awesome. So, thinking back to the examples that we've talked about, the monocular depth estimation, the neural video codec, we've talked about kind of, this process of from getting from research to, real world kind of, touch it, see it on a device. Does that mean that they're products and that they're productized, or is that a further step that you take these products or these projects?
There is a further step. So we are still part of the research team. Whatever we create is deployable. Um, but our focus is on creating a solid research pipeline, a research pipeline of fundamental AI improvements, uh, and also how they can be optimally deployed onto the device. So across the full stack. So we innovate, implement, and create this research pipeline. But while doing that, the product teams also have innovative advances in the architecture, both hardware and software, and we work very closely uh, with the product teams. And by doing a full stack approach in the research team, we are always ready. When the need arises, the product teams can immediately decide to take some of the innovations. Some go very early, some go a little late, but immediately, as very soon, take it and put it into their commercial roadmap, product roadmap. Then after that, it's about scaling across Qualcomm business. That's a pretty big effort. So we focus on the research side, um, building a solid research pipeline, and our product teams are focusing on the product roadmap. We work very closely and collaboratively.
And the form that these products end up taking, like, does that, say monocular depth estimation, would that be built into silicon, or would that be software that's part of a toolkit, or kind of all of the above, depending on what makes the most sense?
Monocular depth estimation is one example. We have a lot of AI technology in our platform, in Snapdragon platform. We have the entire camera, everything which is needed to do camera, everything which is needed to do video processing. So the answer is all of the above. All these innovations like applications, our product teams will take integrated into the products. Uh, Same thing with the uh, full stack innovations. Our product software team takes it and puts it into the roadmap. But we also make sure that we figure out the best way we can uh, put it out into the community, into the world. Like for example, AI Model Efficiency Toolkit. We felt it's important that that's a open source project, so anybody can use it to quantize, to run an integer hardware. We also have a Model Zoo project. Some of the applications we'll just put it out in the Model Zoo, and with some of them we just directly give it to the customer so they can integrate. So it's sort of all of the above.
Okay. Awesome. Well, Murali, thanks so much for taking the time to share a bit about how you see kind of this full stack ecosystem, and getting some of the research ideas into product.
Thank you. Thanks, Sam. This was really great. Thanks.